Welcome to module 16 of database management systems. Till the last module, which closed with the third week, specifically in the third week we talked about certain advanced features of SQL and the formal query language in terms of relational and algebra and calculi, and then we talked at depth in terms of the entity relationship model, the first basic conceptual level representation of the real world that we can do in terms of designing a system. Now, our next task would be to take it to a more proper complete relational database design, and this will have a lot of theory at different levels that we need to understand. We will slowly develop that, and this discussion will span 5 modules, that is will take the whole week to complete. So, the objective of the current module, the first of the relational design module, is to identify features of good relational design. Having done the ER model, we do the ER model, we have the entity sets relationships, we convert them to schema, we have seen how to do that, and immediately we have some design. But the question is it a good design? So, we will discuss about what are the features of a good design, and then we will introduce the formal definition of what is first normal form, and we will introduce a very critical concept of relational database design, the functional dependencies. These are the module outline for that. So, to start with the features of good relational design, let us take an example. Suppose we have seen the instructor relation, instructor entity set as a relation, we have seen the department relation. Now, let us consider that if these two were not two separate relations, if they were all kept in a common relation, that is, all the attributes are kept in the common relation. So, earlier if you recall that your instructor relation was this and your department relation was this much. So, if we keep everything together, of course, we are calling it ins depth, but please keep in mind this is not the same ins depth that we discussed in terms of the ER model. This is just putting these two together. Now, the question is, if you look into this data carefully, for example, if you look into this particular row, if you look into this particular row, and if you look into this particular row, these are rows of instructors who all belong to computer science. Now, earlier we were representing the information of instructor only in this part. So, we just knew that it is computer science, and we represent the information of department in this part. So, given a department name, say computer science, we knew where does it where is it located, the building, and what budget it has. Now, when we are combined, we will see that naturally, since computer science is located in the Taylor building, we know, and it has a budget of say 100,000. So, all of these records will have this information repeated. So, this is not a very good situation. This is not a good situation, because this kind of situation is typically in database is known as redundancy, that is, you have the same data in multiple places. So, what is the consequence of redundancy? For example, there could be different kinds of anomaly when you have redundancy. What is an anomaly? An anomaly is the possibility of certain data getting inconsistent. For example, let us say computer science department moves from Taylor building to Painter building. Now, what will have to happen if it moves to Painter building? Then I will need to remove this, make it a Painter, make this value Painter. I have to also do this, make this Painter. I have to also do this, make this Painter. So, if I have a change, then I will have to make the change at multiple entries. Think about the earlier situation where I just had these 3 in my department relation, then naturally computer science had only one row, and therefore, this change, this update could be done at only one place. So, it is not only that while doing this, in case of this redundancy I have to do this multiple times, it also has the difficulty that if I forget to update any one of them or more of them, then I have inconsistent data. Similarly, if I want to insert a new value, I will have to do that for all this redundant information. If I have to delete, say for some reason, let us say the university decides to wind up the physics department, then I have to delete all this rows which have physics as an entry, and the consequence of that is the department is deleted, but as a consequence of that I will delete the whole row, and therefore, I will not only remove the department, but I will also remove the corresponding instructor who was enrolled for that department. So, this kind of redundancy can lead to different kinds of anomalies in a database design. On the other hand, if you look at why am I complicating the whole situation? We have already had a good design in terms of where these anomalies were not there, department was separate, instructor was separate. In that case, the situation is that to answer some of the queries, I may have to do a very expensive join operation. For example, if I want to know if Einstein wants to know what is the budget of his department, that cannot be found out from the earlier instructor database, instructor relation which had only these fields. So, I have to pick up Einstein from here, do a join based on the department name, dep name with the department table, department relation, and then only I will be able to find out that Einstein belongs to physics, physics has a budget of 70,000. So, Einstein's department has a budget 70,000. So, there is a trade off between how much data information you make redundant and lead to different anomalous situations, and or how much data you optimize in the representation, but get into the possible situation of having a higher cost in terms of answering your queries. So, this is one of the core design issues that we will start with. So, let us look into some more of these examples. Let us say we look into another combination of schema. Suppose section is a relation which have the sections of a course which give the section ID, semester, year, and say section class is another relation which tell me for a section ID what is the building and room number where it is located. So, if we have this kind of relations combined into a common relation, then I have all of these coming from the section and this and these coming from the section class, but we can see that there is no repetition or redundant information in this case. So, it is not that combining schemas is necessarily always bad in terms of repetition or in terms of redundancy. So, different situations will have to be assessed. So, if we want to look at the other side, that if we just as I said that if we make the schema smaller, so that we avoid redundancy, and then what we see that from the combined inst dept relationship that we saw. So, if let me just show you once more. So, this is if we look at the inst dept, then in this we know that from the earlier information about the department relationship, that department name is a key, is a primary key of the relation which has department name, building and budget. What is the consequence of being a primary key? If it is a primary key, then no two records can match on the department name and be different in terms of the building and the budget. If two records are there which have the same department name, they must be identical. So, they are distinguishable completely by that. So, let us see what is the consequence of this, And so, we are saying that we write it as a rule that if there is a schema department name building budget, then department name would be a candidate key. And we write this observation that if two records match on the department name, they must match on the building and budget, and very loosely we will come to the formal definition. Very loosely we call this the functional dependency. We say that the building and budget is functionally dependent on the department name, and that is a situation where we can split this ins depth and create a smaller relationship, because department name is not a candidate key in the ins depth department. It does not decide the records of ins depth uniquely. So, it is since it does not, so it when the values of this key this attribute department name is duplicated or triplicated, the values of the building and budget are repeated and we have the redundancy. So, this is a situation, very common situation, which is indicative of the fact that we need a decomposition into smaller. But at the same time, we can also observe, I mean, let us take a different example. If we are thinking that decomposition is the panacea of solving these kind of redundancy and related problems, then let us try to see a different relationship employee, which has ID, name, street, city, salary, and we want to make it smaller and want to make two relations, ID and name, city, street, salary. So, if we do that, then how do we get the say salary for a particular ID? We will naturally have to join these two, relations in terms of the common attribute name. We have seen that in the query. Now, the question is, when I do this join, do I get back the original information or I lose some information? Look at an example. So, here is an example of the combined instance, and I have two different IDs, but incidentally the names are same. Incidentally, the names of these two distinct employees are same. So, when I decompose, I get this relation which shows ID and name, I get this relation which against the name shows this. But when I try to join them by natural join, I not only get the combination of this with this, which is what I need, but I also get this combination. So, if I say this is what I get as well in terms of natural join, this is what I get as well in terms of the natural join, which are really not there in the original relation. So, you can see that in the natural join I get 4 records, I get 4 rows, whereas in the original one I had only 2 rows. So, I get some entries which are actually erroneous, these are not there in the database. So, this is when this happens, we say that we have loss of information, and such joins are said to be lossy joins. So, while we decompose, we need to make sure that our joins are lossless in nature, otherwise that is not a good design. So, you can see this is again a hypothetical example which shows 3 attributes, a relation having 3 attributes, we have decomposed it into 2 relations having 2 attributes each, and we have shown an instance, and in this case it shows that when I take the join, the original information, I am sorry, wait. When I take the join, the original information is completely retrieved. I get back the same table, and when that happens, I say that the join is lossless. So, what we need to understand is on one side there is a need to decompose relations into smaller relations to reduce redundancy, and while we do that, we will also have to keep this in mind that the smaller relations must be composable through certain natural join procedure to the original relation, and I must get back that original relation, otherwise I have a lossy join which is not acceptable. And also the decomposition will have the costs of doing natural join every time I want to answer those queries. The next that we look at is the way the relationships are categorized as first normal form. We consider that the domains of attributes are atomic if they are indivisible. So, anything that is a number, string and so on is considered to be atomic. And we say a relational schema is in its first normal form if the domains of all attributes are atomic and all attributes are single valued, there is no multi-value attribute. If these conditions satisfy, then we will say that that relational schema is in its first normal form. So, we will slowly understand the purpose of defining such normal forms, but let us initially understand the definition. So, we have if we have attributes which are composite in nature, naturally my relational schema is not in first normal form. If we have attributes which are multiple valued, it is not so. So, if we say that we have possible values are like this, then if we just treat them as strings, then the corresponding relational schema is in first normal form. But if we say that from this string we can extract the first two characters, which is CS, which tells me what is the department, the next four characters gives me a number, the serial number of the particular student in the roll, then I am not actually using an atomic domain, because my domain needs to be interpreted separately than just being a value. So, these are not parts of what can be a first normal form. So, I have given some examples of what is not and what is first normal form. So, this is an example where the telephone number field exists and there can be multiple telephone numbers. So, this is not in first normal form, because the telephone number itself is composite, because it has different components, and also you can have multiple telephone numbers. So, this relation is not in the first normal form. What you can do, you can separate out these phone numbers into two different attributes, telephone number 1 and 2. Even then it is not exactly in first normal form, because you do not know in which order they should be handled. If you have to search for a telephone number, then you will have to search multiple attributes which are conceptually same, and then the question is, why only two attributes? Cannot anybody have 3 phone numbers, 7 phone numbers and so on? So, this is really not a good option. So, the other way could be that for every telephone number you introduce a separate row. Once you do that, you already know you have redundancy and you have possibilities of varied kinds of anomalies that could happen. So, one way it could be achieved is we follow the principle that we had seen in the ER modeling, that this multi-valued dependency can be represented in terms of a separate relation, where against the customer ID we just keep the telephone number. So, we can keep multiple of them and we take that out from the customer name. So, a one to many relationship between the parent and the child, between the customer name and telephone number. Every customer may have more than one telephone number is possible, and that makes it a 1 NF relation, one first normal form relation, and we will later on see that it also is 2 NF and 3 NF, but that is a future story. Now, finally, we come to the core of what the mathematical formulation which dictates much of the relational database design is known as functional dependencies. I just talked about a little bit of that while talking about department name, building and budget. Now, to decide whether a particular relation is good, or rather a particular relational scheme is good, we need to check against certain measures, and if it is not good, we need to decompose it into a set of relations such that these conditions satisfy, that each one of these, so R 1, R 2, R n. So, I mean if you have got rusted, then it is basically R I is a set of attributes, because it is a relational schema. A relational schema is a set of attributes. So, and naturally R will be the union of all of these R I, the total set of attributes. So, instead of keeping all the information into one relation in one table, we are basically decomposing it into n different schemas. And so, what we need to guarantee is each one of these relation R 1, R 2, R n is in good form. And how do I get back the original relation? Original relation that was represented by all the attributes in R is to take a lossless join, is to take a join, and that this decomposition must give me a lossless join. So, to ensure that, we make use of two key ideas, more foundationally functional dependencies and then multi-valued dependencies. A functional dependency is a constraint on the set of legal relation. So, mind you, it is a constraint on the schema, and once that constraint is defined, it must hold for all relations that the schema satisfy. So, here we need that the value of certain set of attributes uniquely determine the value of another set of attributes. So, I know the value of 3 attributes, I should be able to say that values of the other 4 attributes would be fixed. So, you have already seen this notion in terms of key or super key. You have seen that similar type of concept exists, where we said a key is a set of attributes, so that if the values of 2 rows are identical over these set of attributes, then the 2 tuples, the 2 rows must be totally identical. So, key is something which does a similar thing as a functional dependency, but is more specific. Functional dependency is a generalization. So, let us formally define that. Let R be a relational schema, which means that it is a set of attributes, and let us say alpha and beta are 2 subsets of R. Then we say write this and note this notation: alpha is a set of attributes, beta is another set of attributes, both are subset of the same R, and we say alpha functionally determines beta. That is, if I know the value of a tuple over the attributes of alpha, then the values of that tuple over the attributes of beta would be fixed. Or in other words, I say that if I have 2 tuples T 1 and T 2 and their values over the set of alpha attributes are same, then necessarily the values over the set of beta attributes must be same. And mind you, this is something which is a design constraint. It is not just an incidental property, it is not just the fact that a particular instance of a schema satisfies this, but when you say this is a functional dependency, we need all possible past, present and future instances of the schema must satisfy this. So, consider this: if you take a relation, a schema with an instance as given here between 2 attributes A and B, then we can say, at least given this instance, we still do not know what happens in the whole schema for all instances, but on this instance we can say that A functionally determines B does not hold, because between the first and the second record the value of A is same 1, but the value of B are different 4 and 5. But we can certainly say that on this instant at least B functionally determines A holds, because whenever the value, if we take any 2 tuples, the value over B does not at all match. If that does not match, then naturally there is no question of what happens to the value of the tuple over the set of attributes A. So, we will say that B functionally determining A holds in this instance. So, given this definition of functional dependency, now we can have a formal definition of what is a super key. A super key is naturally a subset of attributes which functionally determines the whole set. And a candidate key is a super key which is minimal. So, which means that a k is a candidate key if the two conditions have to satisfy. This condition say that it is a super key, that it functionally determines all the attributes, and the other condition says minimality, that there is no subset alpha of k such that alpha functionally determines R. If there exists a subset alpha of k, the proper subset alpha of k, so that alpha functionally determines R, then k would not be a candidate key. We will have to check for alpha. So, these two, what we had stated earlier in qualitative terms, are now mathematically established. So, we can say that there are different functional dependencies. For example, in the inst-depth combined relationship relation, if we look at, then we know that department name functionally determines building, ID functionally determines building, but so these are functional dependencies that must hold, but certainly you would not expect department name to functionally determine salary, that would be too much, right. So, functional dependencies are facts about the real world that we try to understand from the real world and then represent in terms of the functional dependency formulation in the database. So, we can use functional dependencies to test relations if they are valid under the set of functional dependencies. So, there could be multiple functional dependencies in the set, and if a relation, we are using small r here just to remind you that a relation means that a particular instance is legal under a set of functional dependencies, we will say that R satisfies it. And if we specify, if we have that it holds, f will be satisfied by all possible instances of a relational schema capital R, then we say f holds on R. So, a relation satisfies a functional set of functional dependencies, and a relational schema, for a relational schema, the functional set of functional dependencies holds on that schema, which means that for all possible past, present and future instances relations, that the relations will satisfy the functional dependencies. So, we have for example, ID, we know ID functionally determines name, that if the ID is distinct, then the name has to be distinct, but we may find that instance where name functionally determines ID. So, we can say that it names functionally determines ID is satisfied by a particular instance where it so happens that there is no two rows where the name is identical, but we may not be able to infer that as this dependency holding on the relational scheme as a whole, because tomorrow we can get another entry, so that the two rows might match on the name, but could still be distinct entries not matching on ID. So, that is how this will have to be looked at. In specificity, we say that a functional dependency is trivial if the left hand side is a superset of the right hand side. So, if I have a bigger set of attributes on the left hand side, ID and name, then obviously ID and name will functionally determine ID. ID and name will functionally determine name. Name will functionally determine name. So, if you just think about, because in a functional dependency, the left hand side attributes, the tuples have to match on the left hand side attribute, and if they do, then they must match on the right hand side attribute. So, if the right hand side set of attributes is a subset of the left hand side, then obviously the functional dependency will be vacuously true, and these are called trivial dependencies. So, in the next couple of slides, I have shown a few examples of functional dependencies of different tables. Here student ID functionally determines semesters, which mean that we are trying to model that a student cannot be at the same time in 2 semesters. Then student ID and lecture together functionally determines who is the TA, and so on. And you can see for this particular relation, student ID and lecture pair also happens to be the candidate key. These are another example. So, these are just go through them, try to convince yourself that these functional dependencies are very genuinely real world situations that can be modeled in this way. Given a set of functional dependencies, we can actually compute a closure. For example, if A functionally determines B and B functionally determines C, then we can infer that A functionally determines, because if two tuples match on A determines B says that they match on B. Now, if B functionally determines C also holds, then if they match on B, they match on C. So, if they match on A, then necessarily they may have to match on C. So, this is called the logical implication of a set of functional dependencies, and we will see more of this later, but if we take all functional dependencies of a given set F that are logically implied from this set F, we say that is a closure set, and we represent that by F plus. So, F plus necessarily is a superset of F. So, here in that above example, this is the F and this is the F plus. So, we will continue more on the theory of functional dependencies, but let us conclude this module by summarizing that we have identified the features of good relational designs, trade off between decomposition and lossless join properties that we need. We have familiarized with the first normal form and atomic domains, and we have introduced the notion of functional dependencies on which we will build up more and try to get zero in on very concrete strategies for good designs.